All right. Hello, everyone. Welcome to CS 396 Scalable Software Architectures. I'm Steve Tarzia, in case you don't know me. Let's get started. All right. So today is the first lecture, and I'm recording this on Sunday afternoon. Class is supposed to be on Monday. Hopefully you get to see this before Monday. And today I'm going to go over a few basic things. So first of all, what I hope for you to learn from this class throughout the quarter, how the class is going to be operated, like what you're going to have to do and what different modes of participation we're going to have, and also try to give you some sense of whether you're ready for this class. So in case you're not sure whether you want to stay in the class, hopefully after today's lecture and after having looked at the first homework, you'll get a sense of whether you should stay in the class or drop it. But hopefully you stay in it, because I think there's a lot of important stuff to learn. And I've designed it to hopefully be approachable to most anyone who's taken the prerequisites. Okay, so after that, I'm going to talk a little bit about the Java language, which we're going to be using, and a little bit about Amazon Web Services, which we're going to use throughout the class. And at the very end, I'm going to give a little bit of an overview of the first homework assignment, which was just posted about an hour ago, to help you get started on that. Okay, so first, just some introductions. I'm Steve. We also have 4 other folks helping us with this class. Yingyi Luo is a PhD student in computer engineering. Guanan Zhao is also a PhD student in computer science. And Clarissa Chan and Alex Ri are the undergraduate peer mentors who will be helping with the class. And all of us will have office hours, and so hopefully you'll get to meet all of us remotely before the quarter's over. A little more about myself. I've been teaching for 3 years now at Northwestern. I got a PhD from Northwestern in 2011. Prior to that, I did my undergrad at Columbia, and both my degrees are actually in computer engineering. And my research expertise, which I haven't done much with since then, but in grad school, I worked a lot on acoustic sensing on mobile systems. Like I developed, for example, an app that used the microphone to listen to background sounds to figure out what your location was in a building, to do indoor navigation, because GPS doesn't work indoors because the roof blocks those signals. But after graduating with my PhD in 2011, I kind of shifted into industry and worked at a few Chicago area startups. First as a software engineer, then later as a manager. So I was a VP of engineering at a couple small companies, and did a lot of architecture design. So that is experience that I'm bringing to this class. And also, hiring and like engineering management stuff in addition to the regular software engineering stuff. So hopefully I'll bring to you a little bit of a different perspective than the typical classes that you take as a computer science student or computer engineering student or whatever, because of that industry experience. And in my kind of software engineering life, I published about 10 iOS apps, so kind of focused a little bit on that platform, as well as the kind of full stack and DevOps stuff on the back end. So I've done a lot of stuff with Linux, Amazon Web Services, Java, Python, and Objective-C for the iOS stuff, in addition to other stuff. But those are some of the technologies that I'm familiar with and that I've introduced into this class. I also, just before I started at Northwestern, I did a nonprofit startup called the National Gun Violence Memorial, which is a website that has profiles for every gun violence victim in the U.S. So right now we have like 60,000 pages, and we get a lot of traffic. So it's a pretty good-sized website, and it'll be a case study that we come to a few times in this class, just as a convenience, because I can show you behind the scenes how that works. Outside of that, I have hobbies like anyone else, just so we know each other a little better. I enjoy playing music, so like guitar, drums, and trumpet, and also listening to music, going to the opera, getting exercise, like cycling around Evanston. You might see me on a bike, cooking at home, and just repairing things in general around the house. I've been married 14 years, so right after college, got married, and have lived in Evanston for the past 8 years. So that's a little about me. Hopefully I'll get to learn a little bit about each of you, and I hope that you can look to me as a resource, not just for this class stuff, but also for advice about your career and anything else. All right, so obviously this is an unusual quarter, but the course is going to run not too differently than how it normally does, except for the fact that these lectures are going to be pre-recorded and delivered before our normal class time. So the normal class time is still going to be used, but that normal class time is going to be used for answering questions on Zoom. So this is a Panopto session, which records 2 different video streams and the slides. So that'll be used for you to get my presentations about the topics. I'll try to post these videos at least 24 hours before class time. Now you'll notice that this time I did not manage to get that done because the first lecture is the hardest to get ready because I needed to get all the assignments done and stuff. Anyway, excuses aside, this one's a little bit late, but I'll try to get you these all at least 24 hours before class time so that you can, the idea is to watch the video before class, do any assigned reading before class, and then at class time, everyone can show up and on Zoom, and we can all kind of talk to each other, have a discussion. And I mean, not really a discussion, but primarily, I might ask you some discussion questions, but primarily I'm going to be there to answer your questions about the things I presented in the pre-recorded lecture and the things that you read in the book or whatever other readings that I give you. Okay. So Zoom during class time will be for questions. There is a Piazza page for questions, and that's also a good way to get your questions answered. And I encourage you to definitely use Piazza instead of emailing me directly, because when you do that, then all the teaching staff can see your questions, and also your fellow students, if you enable it, can see your question, and you'll get a much faster answer than if you email me directly, because we have 5 different people working on this class to help answer your questions, not just me. So one other thing I want to mention here, it's maybe kind of obvious, but now that we're taking classes and teaching remotely, you have to kind of learn some new habits to be successful in this new format. And so I'm going to have to learn how to do more asynchronous teaching, although I've been using video tools since I started teaching here. You'll notice if you look on like YouTube or on my website, I have recordings of all my past classes. But for you, like you're going to be watching these videos and you're not going to be able to like raise your hand and ask a question, but I want you to still kind of be able to do that. So what you should do is have some kind of a notepad or a text file available whenever you're watching these videos to be able to write down your questions. So when you have a question, write down like the slide number, some details, what your question is, and then later on you can ask it. You can ask it through Piazza, or you can ask it in that live Zoom session. And usually it's easier to get an answer live rather than typing it up, but either way works. So we're going to have office hours. Those are all going to be on Zoom, and I have office hours scheduled for all of us who are on the teaching staff every day. So in addition to that Monday, Wednesday, 12:30 to 1:50 p.m., when me and Yingy will be available to answer all your questions. In addition to that, we have these Zoom office hours that you can use for one-on-one questions. So it's a pretty decent number of hours. I'll make announcements if these have to change. But you'll find links to these office hours on Canvas in the Zoom section. And the way that will work is, just like normal office hours, many people can show up and you can see each other and talk to each other while you're kind of waiting your turn. But the way that you will put yourself in line to ask a question to the TA or the instructor will be to say something in the chat, because the chat is kind of time ordered. So reserve your place in line by putting a message in the chat saying that you have a question, and then the person running the office hours will kind of scan through that to find who's next after they finish with one person. And they might answer a question kind of openly to everyone in the room so everyone can hear it and benefit from the answer. Or if your question is more like nitty-gritty and related to your particular code where people don't care about it, you're just trying to figure out what this bug is in your code, in that case, they might bring you to a breakout room, which is like a private sub-Zoom session, and work with you there. And then you could share your screen, and then everyone else wouldn't see your screen. You see your code, and you could work on that. And then when finished, in the meantime, everyone else will be waiting in the main Zoom room. But then when you're finished in that breakout room, you could the instructor will kick you out, and then you can go back and find the next person to help. Okay. There are right now about 10 people auditing, maybe, and there might be more later. Anyway, if you're auditing the class, I hope you can learn from this, but the reason you're auditing and not registered for the class is because there was a limited teaching staff. Only 5 of us, and there's only so many questions we can answer. So if you have questions, try to figure them out yourself or ask other students in the class maybe. But don't ask us your questions because we need to focus our time on the students who are registered. But feel free to answer questions on Piazza if you can. That would be a really nice thing to do. So some other housekeeping. We have a collaboration and cheating policy. So this is basically the same as any other class that you might have taken with me, but I'm trying to be very clear here so that there's no confusion. If there is confusion, if you're unsure about anything, you can always ask me afterwards. But I want to encourage you to help each other on the assignments. There's a lot of coding, and figuring out the source of these bugs is tedious, and it definitely benefits. It's definitely good to have a second set of eyes. So I do want to encourage you to get help from your friends. You can talk to your friends about homework and projects. You can talk to people in the class even if they're not your friends. And in doing so, you can look at the other person's code on their screen. Okay, so you can look at small parts of each other's code on the screen. But I don't want you to copy code. So if you're looking at someone's screen and you're typing at the same time, that's bad. You shouldn't do that, right? Because that's copying. If you send a digital copy of your code or any kind of version of your code, whether it's an image or a file to your friends, that's also not allowed, right? Because that's sending a copy that someone can reuse. If you share your screen on Zoom, I would say be careful about this, because you might not know whether the person on the other end is taking a screenshot, and if they do take a screenshot and then reuse your code, and then we'll find that later, and then you'll both get in trouble for that. So I would discourage you from sharing your code on Zoom unless you're actually doing a group project. Don't post your code to a public Git repository. That's kind of obvious, but by default, when you're using GitHub, the default is to make a public fork. So don't do that. If you find code on the internet, for some of the projects, little pieces of it, you'll find code on Stack Overflow or blogs or whatever. That's okay. You can reuse code from the internet as long as it's not a answer specifically to this course's projects. I don't think there are any solutions out there. If there are, and you find them, let me know. But we already looked for those. Anyway, if you find code on the internet, you can kind of copy paste it in, but you should add a comment explaining exactly where you got it. So include a link, a URL to the Stack Overflow post or blog post or wherever. Okay. So you should understand what your code does. And if you don't, and we ask you about your code and you can't explain it, then that means that you probably didn't write it. There's this tool called Moss, which we can use to compare code. So we're going to compare your code to everyone else's code, the submitted code. We'll compare your code to code from the previous quarter when this class was taught, and it's very easy for us to find similarities, even if you changed some things, renamed variables, whatever. If you think you're being clever, you're still going to get caught, so don't do that. And when you do that, you'll get your appropriate dean will be notified, and you'll get in a lot of trouble for doing that. Okay, so just don't do it. And if you have questions, let me know. I mean, pretty much everyone except maybe grad students is going to be on pass-fail this quarter, so hopefully you're not too stressed out about it. But there still is a lot of work for the class. I think that in certain parts you can just kind of get partial credit, and that's a way to kind of get through without necessarily killing yourself, if you're stuck on a certain bug. But do let me know if you're having issues and you want, if you're struggling with the class. Please come to me, and we'll figure out what to do about it. All right, so we have a cheating policy. Fortunately, the dress code policy is much more relaxed. All right, so we're doing teaching at home. I'd like to call it quarantine casual. Okay, so anything goes, and that's fine. All right, and you'll notice also that I got a haircut, homemade haircut. Yeah. We're going to have to get used to that. All right, so the prereqs for this class are data structures. So this is like basic intro CS stuff. Data structures, object-oriented programming. There's a CS213 class, which is like intro to systems. The part of that is important is just that's a class that has a lot of, I think, C and assembly coding. We're not going to be doing that in this class, but you should be familiar with like the command line, Unix command line. Right. I don't expect you to know Java ahead of time. In fact, for most students, you're going to be learning Java for the first time in this class, unless you've taken maybe the databases class or one of the other 300-level classes that uses it. So it's okay I'm expecting you to learn Java in this class, and so that'll be one of the kind of benefits of taking this class, is that you'll learn that language, which is pretty useful. For example, Android apps are developed in Java, as well as a lot of backend stuff at big companies. So if you're not sure whether you're ready for this class, try the first homework. The first homework is actually pretty challenging. So if you have questions, if you're thinking about dropping, maybe ask me beforehand, and I can give you some advice on that. But definitely look at if first homework looks doable, then you're definitely in good shape. If it doesn't look at least somewhat confusing, I expect the first homework look a little bit confusing. Let's put it that way. It's not an easy start. It's a kind of a difficult start. All right. So in the course description for this class, I think it says that we'll be building systems with surprisingly little code. That doesn't mean there's not going to be a lot of coding in this class. In fact, there is going to be a lot of coding in this class. I use that phrase surprisingly little because we'll be building some pretty complex, impressive systems which do some interesting things, but when you look behind the scenes, there's not a lot of code that makes it run compared to what you might expect. So it's surprisingly little code compared to building a commercial system from scratch, but it's not little compared to other CS systems classes. All right, so because we're teaching remotely, there are going to be no exams. So the grading is going to be 100% programming and architecture design assignments. So those are two different things. So the programming is going to be Java, HTML, React, mostly Java, a little bit of web front end thrown in near the middle of the class. And then at the very end of the class, you'll be doing some architecture design documents, which are PDFs that list out APIs and database schemas. This should say some basic, not DOM. I'm not sure exactly the split, but it's probably going to be like at least 60% programming, and then the rest would be the design documents that we do at the end. So there are kind of two tracks to this class, I guess. There's the programming part of it, where you'll be learning Java, you'll be learning how to work with complex APIs and to read technical documentation, stuff like that. You'll learn that through the assignments, and the lectures won't talk too much about most of that stuff. But the stuff I'm talking about in the lectures will be used for the architecture design assignments toward the end of the class. So I guess you'll notice maybe in the first half of the class, the things I'm talking about are not necessarily going to help you with the assignments, which might be a little bit frustrating. Although I'll try to put in more help than I did in the previous quarter, throughout these first lectures that's directly related to the projects. But anyway, we talk about a lot of concepts. You'll be reading about a lot of concepts in the book, how to design systems. But for the first assignments, you're going to be doing a very clearly, strictly defined assignment. I'm going to tell you exactly what to build. You're not going to be doing architecting. You're not going to be designing new systems. You're going to be implementing a system that I've already designed for you, right? So in the early assignments, you're going to be working on your back-end programming skills, basically. But then that doesn't mean you should ignore those first lectures, because those concepts I'm going to be talking about are going to build until eventually near the end, you're going to have a lot of different components, systems, and techniques that you know about that will be needed for the final assignments on designing architectures. And then also, that stuff you're learning is going to be useful when you go into industry and when you interview for software engineering jobs. So I like to say that the final exam for this class is your software engineering interview. Okay, and I've actually got feedback from students. One of my students in the fall actually told me that one of the architecture design assignments that I gave in the second to last homework assignment was literally the question that they were asked at I think Microsoft interview. and she did pretty well on that interview and got the job, I guess in small part because of taking this class, right? So hopefully we have more success stories like that in the future. Okay, so this is kind of a new class. Right now it has a 396 number, which means it's a special topic. But next year it's actually going to be offered as CS 310. It's going to have a permanent number. It's going to count as a breadth class for the CS major in the software development and programming languages category. So this class has been kind of accepted as a core part of the computer science major at Northwestern, which is kind of cool because I think it's important and it's new and it's not something that every university has. Okay, because it's a little bit more industry focused and it's also a lot more like up to date or modern than the typical topics that are covered in computer science classes. Okay, it's easy to teach a class on relational databases using concepts that were developed 30 years ago and textbooks that were written 15 years ago and they're in their 8th edition. You know, it's easy to teach a class on networking, which I teach and I think it's important, but you know, the concepts in that class were, you know, we start with stuff that's 30 years old and we finish at stuff that's like 20 years old. It's important stuff, but it's easy to teach because it's been around for a while. Everyone teaches it because it's recognized as important. The stuff in this class, like cloud computing, software architectures, and scalable components, all that's like the stuff we're learning here, I think is just as important because it's really about how systems these days are all built using these components. But it's a new topic and it's evolving rapidly. There are no textbooks that really cover it really well. We do have a textbook I signed, which is okay, but it's not perfect and it's a little bit dumbed down. So developing this class was a challenge. I think it's important. So the class is not going to be, I would say, perfect. Compared to teaching, say, operating systems or networking or databases, there's much less, like, there are fewer resources out there that I can draw from. I have to build more from scratch, like all these assignments and like pulling readings from various sources. But so it's a little more work for me. It's a little bit less organized for you than a traditional CS systems class. But the end result is that you're getting something that's more up to date and that's more directly applicable to the work you'll be doing, and also that gives you a competitive advantage compared to, I think, other graduates from other universities. Although some other universities have some cool new classes that are kind of similar. I've never seen something exactly like this. So in your traditional CS curriculum, everyone learns in the first few classes how to write programs. And I'm using the word program here to mean a single executable or process, so a code that runs on a single machine, usually a single threaded. If you're taking an OS class, you know what that means. So basically, it doesn't have any parallelism. It only does one thing at a time. It takes an input and produces an output. And so those are when you're working on that kind of a program, the things you care about are correctness, like producing the right output for that every input, efficiency, like the amount of time it takes to run, and also, hopefully, although this is usually a secondary consideration, but you would want the design of the program to be clear enough to easily understand what's going on and to be able to write it quickly and to be sure that it doesn't have bugs, right? So those things are kind of covered in most CS classes. And then at the upper level of most CS classes, we go into different research areas, like maybe machine learning or graphics or networking, HCI, stuff like that. These are basically intros to PhD programs that are doing research. But it's hard to find a class that really teaches you how to build more complex software systems apart from these single machine, single threaded programs that you developed early on. So this class, on the other hand, is trying to do that. So now that you know how to write a program that does something, we're going to learn how do you take a bunch of programs that do various things and stick them together, and also how do you start with a problem, like some task you want to solve, some company you want to build, like let's say you want to build the next Uber. What are you need to map that out, figure out what all the different programs are you need to write, where they're going to live, how they're going to interact, how they're going to share data, and how to run them. Yeah, so that's kind of what we're covering in this class. So this is preparation for a software engineering job as opposed to preparation for a PhD program. But the two are not, they're not totally separate tracks, right? Career tracks, those kind of intertwine. So I'm developing this class, or I did develop this class to try to address the fact that most CS graduates are typically not ready for a real job. So I'm sorry to say that when I was a VP of engineering, I would very rarely interview new CS graduates because they didn't have the skills needed to actually be productive on the first day, or in the first month, or the first couple months even. And like the companies I was working at were small enough that we didn't have the resources to invest like a whole year in training someone before they were going to be productive, right? It would be nice if the universities actually did that training, right? All right, so let's do that here. So I kind of already covered this, but you're going to learn how to build real complex big software services. So not just like not just programs. Like this isn't about writing better code. This is about putting together lots of different pieces of code to build a system, right? You should be able to write efficient code, but you learn that in other classes. You've already learned that, hopefully, and you'll continue to learn that. It's not a trivial task. I don't want to say that writing code is not important or not interesting, but that's not exactly that's not all there is to software engineering. So in particular, when you're building a big system, it's not just about knowing the language and structuring functions and classes in the right way, right? You're going to have multiple apps, and you'll need to coordinate in some way. So you need to design those interactions and interfaces between them, like network APIs, stuff like that. Just decide whether you're going to push data or pull data. Figure out some way to scale load. In other words, if you have a lot of work to do, like you have millions of users who are trying to work at the same time, how do you handle that? Because obviously you're not going to have one computer that handles all those millions of users. You're going to have lots of computers running lots of code in parallel. So you need some way to coordinate that. You also are going to have a ton of data that needs to be modified in parallel by lots of different code running in different places for different users, but then also coordinated so that somehow eventually the data that's being added in lots of different places is made available to everyone else. So for example, when you're using Google Maps, you have a lot of users who are navigating from point to point. There's some database that has information about the best ways to get between places, and you can imagine that that software in parallel to handle those requests for navigation, they each are kind of asking this shared database different questions about how to get from point to point. So that database, it's pretty, I guess, somewhat easy to imagine how you can build that kind of a database by having many copies of the same data that is available on lots of different machines. But then it gets a lot more challenging when you want to start updating that database, right? So as you're navigating, you're also providing new data to be used in the future. So when I navigate from Evanston to a museum in Chicago, let's say, I get a route and I start driving. And as I'm driving, the Google Maps app will record how long it takes to go through each block, right? So it records my speed, and that speed information will be used later on to determine to build a model for how slow traffic moves in different places of the city, right? So we want to be able to actually upload that data and update the model for everyone to use later. And that's a very challenging problem. All right, so to kind of recap the goal for this class in a different way, I want you, when you're done with this, to have enough knowledge to be able to build your own scalable startup product. So if you have an idea for a startup, or you have a friend who has an idea and you want to get together, like 1 or 2 people, 3 people, whatever, and build something without having someone else who's older and has more experience helping you, if you want to do it on your own, I hope that by the end of this class you have basically enough knowledge to do that, right? Just knowing Python or C, like knowing the language, how to use the language to write a program is not nearly enough knowledge to actually build a product that has mobile and web users and all that stuff, has databases. All that kind of architectural stuff is typically learned on the job. at an internship or your first job where you're joining an existing system, you kind of see how it's built. Like you might join Facebook and see, although that's kind of in some ways it's hard to do that if you join a big company because the systems they have are so complex, right? It's hard to learn general principles from something that's like very, very, very complex. But if you were to join, but you still, that's how most people do it, right? You join a company, you kind of see how it's built, and then you use that knowledge later on to build new stuff. But in this class, we're going to go through those exercises together, and we're going to start with pretty simple systems to make that easier. Okay, so that's some of what you'll learn. What you won't learn is much about machine learning. I just mentioned that because everyone wants to learn machine learning. Sorry, there's not going to be a lot of machine learning in this class. We're going to talk about databases, but we're not going to talk about the internals of how databases are built, like how indexes are built and stuff like that. So there's a databases class for that purpose. We're going to talk about cloud computing, but we're not going to talk about some of the foundational technology like virtualization. That's more of a computer architecture and operating systems topic. And we're also not really going to talk about the details of distributed systems. Distributed systems is actually a very closely related class, and I was thinking about, when I was designing this class, I was struggling a little bit to like separate what topics I should cover and not cover. So I've made a choice to not duplicate anything that's in the distributed systems class, although some of it is closely related. So we're going to talk about services. Those are sometimes called, these days most often they're called microservices. So how to have separate like pieces of code running that you can ask to do stuff for you. We're going to talk a lot about different kinds of databases and data stores in general, and like what the differences are. Why are there so many different kinds of databases? This is actually a question that most people in industry, even with a lot of experience, would have trouble articulating because they haven't like sat down and thought about it. They would probably be able to tell you like what the different databases give you, but we're going to try to go through it in a structured way just to like really justify why there's so many different kinds of databases out there. We're going to talk about caching and content delivery networks as an example of like how to scale up a system. Just message queues are used for asynchronous coordination. And then we'll talk a little bit about parallel processing with MapReduce and Spark. I'm not quite sure how much we'll get into that, especially since this is a 9-week quarter instead of a 10-week quarter. So I think maybe this is a topic that's going to fall off a little bit because of the shortened time, unfortunately. I'm going to try to use case studies as much as possible because I think that makes the class interesting and makes the topics more clear. So we're going to look at Wikipedia, some stuff from Netflix, Twitter, and some other companies as we proceed to see how their systems are built. And like, usually we're not going to go through like the whole architecture of any one company, except we are going to do that for Wikipedia. But for these other ones, we're just going to look at like one problem that they have and how they solved it as a case study. All right, so this class like kind of draws from a lot of other older classes, including networking. So from networking, that 340 class, we talk about, in that class, we talk a lot about HTTP and a little bit about REST APIs. So that's something we're going to reuse here. It's again, for all of these, it's okay if you haven't taken the class. I don't expect you to. These are not prerequisites, but there's a little bit of overlap. If you've taken any of these classes, actually, those will help you in this class for sure. And if you really like the topics of this class, then I would encourage you to try to take as many of these classes as possible, but you're not going to have time to take all of them, right? Anyway, so moving on, operating systems class covers processes and threads, and we'll kind of like, and some performance issues that we kind of will cover. Databases obviously covers relational databases, but we're going to talk here about additional types of databases, and we're not going to look so much at the internals of relational databases. In programming languages, that class talks about functional programs, and actually here we'll see with like React and MapReduce how that is. Basically in this class we're going to see a lot of different programming models, which would have been introduced in the programming languages class. So we're going to program in a lot of different styles to handle different parts of the system in the best way possible. And then 345 distributed systems is a class that talks about the theory behind building a system that gets one task done on a lot of machines, and it focuses a lot on the communication between those machines. For the most part, we're going to assume in this class that we already have some off-the-shelf systems available that do communication and coordination of using these distributed systems principles. So basically, this distributed systems class will give you more of a low-level understanding of what's going on in these big high-scale internet systems. So this is an important class, distributed systems is, but it's a little bit, I would say, more low-level focused than this one, and has more theory. Okay, so we do have a book for this class. This is the first time I'm using this book, but I read through it, and I think it's good. It's a little bit, I would say it's a little bit easy for a Northwestern University class, but it's good. It covers, the thing I like about it is that it actually covers pretty much all the exact topics that I wanted to cover for this class, and the fact that the title kind of matches the title for this class is no coincidence, right? The book's from 2015, which is a little bit older than I would like, but actually the content is, the author at that time was very up to date, so it's actually still up to date today for the most part. It doesn't mention like Node.js, for example, but when going through examples, but like it's just really like some of the examples are a little bit out of date, but the principles and the designs are definitely still relevant. And for most of you, the stuff that they're talking about in there is going to be very, very new, even though it's 5 years old. So we're going to read everything in this book except chapters 2 and 9. And I'm going to post in Canvas reading assignments that kind of tell you what you should read before each class time. All right, so right now I assigned chapter 1 already. That's due on Wednesday. I mean, I'm not going to quiz you on it, except that we should all stay up to date and not fall behind, so that you get through everything and you can ask questions at the same time other people are asking questions on that topic. And then, like I said, the final couple of homeworks on architecture are going to draw from all the stuff we're covering in the reading and in the book. There's another good book that I'm showing here, which I used last time. I only used about half of it. You can see the chapters I list here are the ones that cover the topics of this class. It doesn't cover as much as the one that I required, but it's a good read, and it's not expensive, and it also is actually available for free from the Northwestern Library in digital form. So you can check that out as well. But I'm not going to assign anything from this book. I'm just going to kind of leave it out there as a suggested reading. It goes into more details of actually some of the topics that are covered in the distributed systems CS 345 class. And like I said, some of that stuff, I'm not covering that stuff in this class because it's already covered in that other class. Okay. So let me talk a little bit about Java, since for many of you, maybe most of you, this is the first time that you've used it. I'm sure you've heard of it, but you may think of it as an old language that you don't need to learn because it's out of date. But that's not true. Okay, so it was first released in 1995. But the fact that it's still around and still being used for things like, the latest Android apps suggests that maybe it was actually pretty well designed and it's been well supported. So the things I like about it are listed here. So portability, performance, stability, dependency management, strong typing. The fact that the language has been updated to be modern, and kind of the widespread adoption. I'm going to go through each of these in a few slides. Another thing, so apart from the actual technical merits of the language, just the fact that it's a popular language is itself a good thing, because it means that there are a lot of libraries available, and you can look for answers on Stack Overflow to common questions, and someone else will ask the same question before. And knowing it means you can go out and find a job where you can use the language, right? So portability with Java this is maybe the most unique thing about Java, I would say. Java code is compiled to bytecode, and then you run the bytecode on this thing called the Java virtual machine. That's pretty weird. So you're probably familiar with compilation from C or C++, right? Where you write some C code and you compile it, it creates a binary, you run the binary. Some languages are not compiled, right? They're interpreted, like Python or JavaScript, right? You just write the Python code and then you run it through the interpreter, and it just runs without first compiling it. but what's actually happening is it kind of compiles it in real time. But anyway, there's not this compilation step. So, but what Java does is it does have a compilation step, but what it produces is not code that is customized for your machine like what C or C++ does. It doesn't produce machine code. It produces this bytecode stuff, which is kind of like an assembly language for a virtual machine called the Java virtual machine, which is like an abstraction of a machine. So it's not like Intel or ARM or PowerPC or anything like that. It's not a specific instruction set architecture. So if you're a computer engineer, or you've taken an intro computer engineering class, you know what that means. But instead, so it's compiled to bytecode, and the bytecode is interpreted at runtime in the virtual machine. And every platform that runs Java code has a virtual machine implementation that you can install that lets you run code that's been compiled by others in Java on that machine. So when you compile, you produce something that the code that you compile is the same, is universal regardless of what platform you're using. So you can write your code and compile it once, and that compiled artifact can be run on any different platform, even if those machines are very different. Okay. And it turns out actually, so this Java virtual machine now is actually a platform that's been used for other languages like Scala and Kotlin, are more modern languages that are kind of derived from Java in a way. But anyway, they compile to the same bytecode that runs on the same JVM. So this JVM is actually a common like computing platform for a lot of backend code these days. Yeah, so I mentioned already the alternatives. C or C++ compiles to machine code. That code is specific to a particular type of computer, whether it's a like laptop or a particular type of smartphone. And if you compile C code for your laptop and then try to move it to a smartphone, it won't run because it's not using the same machine code language, the same instruction set architecture. Python and JavaScript, technically you can move it to a totally different kind of machine because it's interpreted at runtime. But it turns out that the compatibility is much less than Java. Well, I'm going to come back to that in a second. Okay, so Java has pretty good performance. It's not the best it doesn't have the best performance compared to other languages. Languages like C, C++, or God forbid Fortran are probably the fastest options aside from like writing assembly code from scratch. If all you care about is performance, then you'll use one of these very low-level languages. But those languages have pretty poor developer productivity. Like it's kind of hard to write in C and C++ compared to Java. They have less support for things like inheritance and functional programming. Memory management is a pain, and you can have a lot of memory management bugs in C, which don't happen in Java. There's also a lot harder to use third-party libraries in C++ compared to like using Maven in Java. We'll see. I think you'll experience that throughout this class. Yeah, so Java is a bit slower than C++. It's about twice as half the speed, twice as slow. But the performance is still a lot better than Python on average. So Python is maybe 10 times slower than C++. Java is about twice as slow. Okay, so what Java gives you is good performance, not the best performance, but good performance combined with good developer productivity, much better than what you get from C++. And that's why it's a common choice for backend systems where you do want good performance, but you can't sacrifice developer productivity. You want to give your developers a tool that will allow them to develop code that has quickly, that has a few bugs. And so one of the things that has kind of boosted Java's popularity was the introduction of some good dependency management tools, specifically through Maven. So dependency management is just the general idea of like being able to manage libraries. So you're probably familiar with like npm for Node is a package manager that lets you like install third-party packages. Similarly, Python has pip, right? In Java, there's Maven. And the nice thing about Maven, even compared to those other two systems, like the JavaScript and Python system, what's even better about Maven is that it kind of always works, because the libraries that others have developed are compiled to bytecode, which is universal for any platform, and there's much less chance that it tends to just to work on any system as opposed to having like runtime exceptions. Like with Python, or compile time exceptions. With Python, when you pip install a library, there's often some compilation that happens there, which could fail if your system is not set up in exactly the same way as the original developer's system for that library. Anyway, so the Maven Central Repository is like a website. I guess I can show it to you, which lets you look for libraries. Like for example, if you want to do quicksort, here's a library that has quicksort in the name. Although this is probably a little bit too specific to find a library. But I mean these don't really have any descriptions. You kind of have to know what you're looking for. But yeah, these are available centrally, and using the name. There are two parts of the name. There's the group ID, which is kind of like the company name or the organization name, and there's the artifact ID is a specific library, and there's a version number. Those three things together uniquely identify a particular jar file, which is like the compiled Java archive. And if you have, so this XML code on the bottom here defines a dependency for a specific version of this JSON library, and whoever uses this definition of the dependency will get the exact same copy of that library, and it should just work seamlessly without any like issues. All right. So when we compare that to Python, I mean, Python kind of like offers dependency management in a way that sounds like it should be just as good, but in practice it isn't. I mean, I guess that my guess is that some of you have tried to pip install things on your machines, and they just didn't work for whatever reason. You get these cryptic like compilation errors because Python, and the reason for that is that Python is not like Java, designed with designed to run on any system with this bytecode layer in the Java virtual machine. So ideally, if you're developing a Python library, or sorry, Python code that uses libraries, you can run pip freeze to generate a list of all the things that you pip installed, and you can distribute this requirement set text file that's generated to anyone else who wants to use your code. So someone downloads your repository, they also get this requirements set text file, which tells them what libraries they need to install. They can pip install those, but this often fails due to different C libraries being present or your environment just being slightly different. The problem is that this pip install process actually does a lot of complex compilation and whatnot. When you compare that to Maven and Java, all Maven Java does is download bytecode. It doesn't have to compile anything. It just downloads literally the code that's already been compiled by someone else. It's been compiled in such a way that it'll run on any Java system. That's the advantage. I hope that makes some sense. This is a relatively complex topic, so I realize that I may not be explaining this in enough detail to fully understand it. So please feel free to make a note of your questions here. All right, so another nice thing about Java is that it's stable. The first version was written in 1995, and code that was written for Java version 1.0 can still be run today on the latest JVM. Right? That's certainly nice. You don't want the code you write to be obsolete. If you write code in, if you were writing a lot of code in Ruby 5 or 7 years ago when that was popular, nowadays there's a lot less Ruby code being developed. So yeah, you can still run it, but 10 years from now, will you still be able to get the latest Ruby runtime system for the latest OS? I'm not sure. Java, on the other hand, like I said, it's been around forever. A lot of code's been written for it, so that you can guess that in the future there's going to be support for running Java code, more so than pretty much any other language except maybe C or C++. All right, so yeah, most new programming languages are abandoned within 10 years. So Java's not one of those, so we know it's going to be around. Also, like when you compile a C or C++ binary, you have to, I guess, have taken the operating systems class to fully understand this, but it's compiled to use system calls that are specific to a particular OS kernel, and so that binary won't work when you upgrade your operating system. You have if you do a major operating system upgrade, like minor kernel updates don't change the application binary interface, which is like the system call interface that programs use to interact with the system. Like if you're going to print to the screen, you have to actually do what's called a system call to do that, which is like a thing that the OS does for you. But anyway, yeah, Java code, the JVM is stable, and old Java code still runs. All right, so, but that said, I mean, Java has become less popular over the past few years as other languages have become more popular, and there have been more programmers that have joined the industry, and most of those new programmers have used languages like JavaScript and Python, which are kind of like better suited to most of the tasks that most people need to do. Right. So the blue line here is Java, which has just dropped in popularity over the past. This is a 5-year period. C++ has been pretty stable, but it's much less. This popularity is with Google Trends, which basically shows the frequency of Google searches using these terms. So it's not the best indicator of popularity, but it just gives a general sense. And JavaScript's also been stable. I guess recently Python is among the big languages. Python has gained the most user adoption. All right, so nowadays, so modern Java is actually a lot better than the original Java, and like when you have conversations with others about Java, they might be thinking about the old versions of Java and not realize some of the nice new features that the latest versions of Java have. I think the latest version of Java is either 10 or 11, but this is an example of something introduced in Java 8 about at least 5 years ago. I don't know exactly, 5 or 7 years ago, something like that. Anyway, so at the top here, I have some code which is like written in the traditional old style Java syntax. I mean, actually, this for loop has a thing that was introduced in Java 7, which is like a collection enumeration thing where you can iterate over a collection. But other than that, it's like pretty simple old style code, similar in syntax to like C. But this function, it's called average professor age, old Java style. Okay, so it takes in a list of people called staff, and it figures out the average age of professors that are in that staff list. But not every staff person is a professor, so it does some filtering, like it does an if check to see whether that particular instance is a professor, and if so, it increments the variables that are needed to calculate an average. And then at the end, it returns the average by dividing the sum with the count. But there's a special case if there were none, because you don't want to divide by 0. If there were 0 people in the average, then you actually want to return 0 in this case. That's what was decided. So this is the code to do that. It works and it's understandable, but it's kind of long, right? So someone who's used to a more modern language, like let's say Python or JavaScript, could do this in less code. But with Java 8, we actually get those functional capabilities that modern languages have to get this done quicker and with less chance of a bug. So in the more modern version of this function, we still take in a list of staff member people, but we use a functional approach to filter it and then average it. So we take the list, the stream function turns it into a stream which can have filters and other like functional operators applied to it. So we apply to it a filter, and then in green here we have a lambda function, which is an inline anonymous function, which is defined. So we take every item and we call isProfessor on it, which will return a true or false, and that is used as a filter to just filter out the professors. And then from that resulting stream, we apply a map to it. So we take each professor, and again, we use an anonymous inline function to map from the professor to the age of that professor, shown here. Okay, so now we have a stream of ages, and then we compute the average function on it. And average actually returns an optional type, which is a kind of Java like templated type, which either has a value or it doesn't have something, right? It's optional. So this or else 0 means that if there's not a value, if there's not an average available, then it returns 0. So this code here is shorter, and if you understand this syntax, it should be easier to understand, or maybe not, but it's shorter anyway. And for certain things, this makes the code a lot easier as opposed to this kind of ugly, like iterative approach to programming. So you can do functional stuff in Java, which is cool. Another nice thing about Java, in my opinion anyway, is that it has strong typing. And this is something that makes it different than Python and JavaScript. So when you're writing code, every variable, function parameter, return value, those all have to have a type defined, like very explicitly. So this can slow down your code, but it makes it much more clear what your functions are doing, right? So it makes your code self-documenting. And that's an advantage when you're building a large system where many different programmers have to coordinate. So with a Java function, I don't necessarily have to read it, the implementation, to understand what goes in and what comes out of it, because the function declaration more clearly says that. So here I have an example with two different versions of the same function that I defined in the previous slides. This is average professor age. So for the Java version, the difference is I have explicitly double listed as the return type. So I know that it returns a double. And I know that it takes in a list of person objects. So that tells me if I'm going to use this function, it tells me what I need to provide and what I'm going to get back. Whereas the Python version, it doesn't have that, right? I mean, there's actually a typing extension to Python that I would encourage you to use, which actually introduces this, but it's optional. Yeah. I mean, of course, this isn't a strict contract because you still don't know what it's doing exactly. Like you need some documentation, or you'd have to look carefully at the name of the function, plus the documentation to figure out like what it's doing with this list and what kind of a double it's returning, but at least you know what goes in and what comes out. Okay. So another quick topic I'm going to mention today as part of this introduction is cloud computing. So we're going to be covering that in depth in this class. But the basic idea is that instead of buying and running your own machines, you kind of rent machines from someone else. So someone like Amazon or Microsoft or Google. And they have all these machines in data centers, which are like warehouses with lots of computers and network connectivity. And you can use it for your own purposes and kind of like pay by the hour or by the byte or whatever the unit is. Okay. So there are many of these public cloud providers are cloud computing providers that rent out capacity to developers. And what you get from them often is a virtual machine, which is like not a real machine, but it's a share. It's kind of like a process that's running, like a program that's running on a real machine that provides a sort of like a simulation of a machine that lets you run, for example, an operating system and whatever code you want on that. So you get a machine that you get a virtual machine that you have full control over, that you can reboot and install whatever software you want on there. You can choose whatever operating system you want to have on there. It can be connected to the internet and accept requests, like to act as a web server, for example. But it's not necessarily a full machine. It could be actually just a very small, it could have just a little bit of time or a few cores on a big, powerful machine. And in that way, you can have lots of virtual machines, like hundreds even, running on one real machine. And that makes the cost of each of these individual machines very low, which is useful, for example, for a student who wants to just experiment. And it gives you a lot of flexibility, even as a big company, to have a lot of like little resources that come together, and allows you to flexibly grow your system as you need. You can, using the web interface or a programmatic interface, you can get new virtual resources whenever you need them and get as many as you want, as long as the public cloud provider has the capacity for you, they generally do, unless you're like huge. If you're Netflix, for example, running on AWS, like you're probably using like 50% of their capacity for certain things like network bandwidth, so you might want to talk to them before you decide to double the size of your service. But for most of customers like you and I, we're only going to be using a tiny fraction of the public cloud providers' resources anyway. So in theory, not in theory, but in practice, we have sort of like the unlimited capacity to expand our system to, like, instead of having one machine, then the next day we can have 1,000 machines, and we can do that in very little time without having to go through the process of, like, buying machines and setting them up and all that. Okay, but like again, we're going to talk a lot more about this later. I just want to give you an introduction because you're going to use AWS in the first homework assignment. So another quick note, as you're taking this class and listening to my lectures, I'll try to be as engaging as possible, but I know that sometimes it can get boring, but still, please try not to multitask and pay attention. Otherwise, you might as well just be doing something else. And also, it really helps. This may seem strange for an online course, but it helps to take notes with pencil and paper when you're in class, even if it's on a computer, because it slows you down and it makes you like focus. It makes your brain engage more. So if you're actually typing, for example, typing notes is okay, but it's actually not as good as handwritten notes. Because when you're typing, you can probably type as quickly as I'm speaking, and so you could actually transcribe everything I'm saying. But if you're doing that, you're not actually thinking about what I'm saying. You're just kind of working mechanically. If you're writing with a pencil, you have to actually translate every one of my sentences into like a few words, or translate 3 sentences into 1 sentence. You have to condense what I'm saying. So you have to summarize it in real time as I'm talking. That requires you to engage with the topic and to think a lot more than if you were just typing, or if you're just listening and doing something else entirely. If you're texting with your friends, obviously, then you're not going to be, you might be hearing what I'm saying, but you're not really learning from it. You're not going to remember it. Yeah. So you may ask, okay, if I'm writing notes with pencil or pen, isn't that like useless because I can't search through them later and I can't reformat them? Like, isn't it much better to have a typewritten copy of notes so that it's easier to save an index, right? So I agree with that. And so I have 2 answers for that. First is, actually, the reason to take notes is not to refer to them later, but to remember things. Like, ideally, to learn this material means that you'll just remember it later. It doesn't mean you have notes that you can refer to later. Okay. So the goal of taking notes is actually not to have something you can read later. In my mind, the primary goal. In a class where I'm giving you the videos, I'm giving you the slides, like you already have a record of this stuff that you can refer back to later. The thing you can do by taking notes with pencil, though, is to create a permanent memory in your head of that material so that you don't have to go back and read the video, watch the video, or read the slides, okay? And the second thing is that if you do want the typewritten notes, what you could do is translate afterwards. After class is over, you could type up your handwritten notes. That's something that I have done for certain things, but obviously it's more work. Okay, so we're almost at the end here. I have no idea how long I've been going because I don't have a clock in here, but we'll see. It feels like a long time. But the last thing I want to do is go over a little bit of Homework 1's architecture, just so you understand kind of what it is that you're supposed to be building. So let me switch this. So I'm going to switch to document camera. Okay, it's one of my toys. So in Homework 1, you are going to be building like a data import tool. Let's call this the data importer. This is a Java jar, which basically you can run on the command line. And it takes, so the inputs, it takes as inputs the environment variables. I guess this isn't, which is explained in the project. All right. So but as an output, what it does is it writes the it's not really an output, but it's really a side effect. Because you don't get this output on the command line, but it's just something that happens in the background. As a side effect, you're going to write some data. You're going to put some data, which are actually, in this case, documents, which are news articles, in a database. This is specifically a Elasticsearch database. And there's a thing called an index here, which is like a table that has a bunch of documents. So these documents are the articles. And these documents are going to be like essentially like JSON things. So this is the code you wrote. It stores data in this Elasticsearch database. This is all there, but it's running in two different systems, right? So this is like your machine here, or it could be it could also be an ECS machine, or let's say Northwestern, because ECS department no longer exists. But this over here, on the other side of this squiggly line, is AWS. So this is in the public cloud. So this database is not on your machine. It's somewhere on the internet. It's in a data center somewhere. You are using the network, the internet, to send data to this database. And you're using the AWS web interface to create this thing in the first place to be ready to accept this data. So this is going to be somehow stored like under your account. So this is like sorry, this is really sloppy. In future, I'm not going to write this. I should be able to write more clearly than this. This stuff here, this Elasticsearch database is in your Amazon account. Also in the cloud is another thing, which is the common crawl S3 bucket, which is another database. Okay? And you are going to get from this a bunch of news articles. Okay? So this is basically a database that has copies of stuff on the internet. Like it's like a web archive. So, and this is also on AWS, but this is on a different account. It's not your account, but you have read-only access to the data on this. So this is in the cloud. So your program is going to use the internet for two different things. It's going to use the internet to ask this database for. It's going to basically download a file. This is a not really it's a kind of database sort of, but it's like a remote file system. It's going to download a file from here, a big file, like 1 gigabyte. That has a bunch of news articles in it. It's going to unzip it, basically. And each one of those articles, it's going to load into this database. So it's a pretty simple task. So you have a data importer. It takes a file from somewhere on the cloud, like that was posted by this nonprofit organization. It parses it, splits it up, transforms it, and stores it in your own database so that you can use those articles later to build a news article search engine. Yeah. Okay, that's just a very basic overview. There's a lot of text in that homework assignment, and so read through it carefully and read through it a few times and ask questions. Okay, so your first tasks are to get the book. You should already have it because I emailed you a week ago about it, at least a week ago. The first chapter should be done by Wednesday's class. That's when I'm going to start talking about really some of the first topics in this class. I want you to start the first homework because it's due in less than 2 weeks. It's due on a Friday, not this Friday, but the Friday after. If you have questions from this class or from the reading, bring them to class. Although if you have questions about the reading, maybe wait until Wednesday's class because that's when that reading is due. Okay, but if you have questions about the homework, for example, questions about what I talked about here, about Java, whatever, let's talk about this tomorrow. We can have a little discussion about programming languages. Maybe you can tell me why Java sucks. I'd be interested to hear if you do have experience and then don't like it. But like I said, I do like Java, so be ready to get to hear my response. Anyway, so that's it. See you later, and I hope this recording went relatively smooth.